Okay, we'll go ahead and get started. Can everyone hear me and see the slides?
Yes.
Thank you. So today we're gonna start covering chapter 9, but before we start on that, I just want to mention a couple things. One is that on Monday you'll have exam number 4, and that covers chapters 7 and 8. The other thing I wanted to mention is that next week, probably towards the later in the day on Wednesday. Next week, later in the day on Wednesday, I'll send out a quiz, your last quiz, and that will cover chapter 9, and that'll be a take-home quiz. So that quiz on chapter 9 next week will I'll send it out maybe later in the day on Wednesday, and then it'll be due by Monday. And then the final thing I wanted to mention was, for those of you who are in my lab section this afternoon, remember that that's an online final exam. So be sure and log on sometime during the class time and take the exam. For those, I've had some questions from students who are in other sections, whether it was going to be in person or online. I would say check with your instructor to see how they're doing it. I think for the most part, the other instructors are doing it in person, but check with them to be certain. Any questions about any of that stuff, about the exam on Monday, the quiz next week, or the lab final? Okay, so let's go ahead and start chapter 9 then. And in chapter 9, we're talking about molecular geometry and bonding theories and things like that. So a lot of this hopefully will be familiar to you because we touched on it in the last lab, that last computer lab, where you had to do some of this molecular geometry stuff. Hopefully you'll understand it a little bit going in and understand it even better when we're finished. So when we have been talking about Lewis structures, and so that's the dot structures. The Lewis structures are helpful in understanding what bonding is going on, because we have representations. We have representations for the bonding electrons. We have representation for the lone pairs, so that's the dots that are free. But it really doesn't give us any information about the geometry or the shape of the molecule. And that geometry or shape is important because it imparts some of the physical and chemical properties, and also gives us some clues on how things will react based on the shapes of the molecules. So Lewis structures, while it shows that bonding and electron numbers, it doesn't give us any information on that. We can use some of that information to help us determine the shapes, though. And so down at the bottom of this slide, we have some shapes that are seen for central atoms that have 2 or 3 other atoms attached. And so we see if there's 2 atoms attached, we can have a linear shape, we can have a bent shape. For 3 atoms attached, we can see that we can have a trigonal planar. So in other words, it's a flat triangle looking shape. And then we have a trigonal pyramidal. So it's still a triangle shape, but the central atom is raised a bit out of the plane of the other atoms. And then finally, a T-shaped arrangement. So what we're going to do today is we're going to talk a little bit about why we can have the same number of atoms attached, but yet we have a different physical shape. So when we talk about the shape of the molecule, really what we're talking about are the bond angles. And so once again, bond angles are one of the things you measured in that last lab. And in terms of the size of the molecules, that's where the bond length comes into play. But shape is more the bond angle issue. One thing we want to remember is that electron pairs repel each other. Because remember, we talked about we have electron repulsion that can occur. And so when we have these different electron pairs, whether they're a bonding electron pair or a free electron pair, there's going to be repulsion amongst those different electrons. And so the electrons, because of to minimize the repulsion, want to be as far apart as possible. And it's that repulsion that factors into the shape that we see of the molecules. When we talk about this, there's something called valence shell electron pair repulsion. And that's a model that was developed to kind of explain these shapes. People rarely say it all out. They usually go by that acronym VSEPR, and that's usually called VESPR. So this VESPR theory helps us understand the shape of the molecules and why they have certain shapes. So we're going to talk about VESPR a little bit next. This was one of the things you had to determine in your lab, but we discussed this in terms of electron domains. And electron domains can be either a single bond, it can be a multi-bond, double or triple, or it can be free lone pairs of electrons around that central atom. So in this example, this AB example, we see that there are 4 electron domains. 2 of them are represented by that AB single bond. One of them is represented by the double bond of A to B. And then the last one is represented by the lone pair of electrons on A. So whether it's that single bond electrons, it's the double bond electrons, or it's the free electrons, the free electron pair, each of those are considered an electron domain. So in this example, there'd be 4 electron domains around that central molecule, central atom of the molecule. So when we talk about the VESPR model, what we're trying to achieve is the best arrangement of the electrons that minimizes that electron repulsion. And so in these balloon examples here on the right, we see linear orientation, trigonal planar, and then tetrahedral. And we see that by arranging them in this fashion, we minimize that electron repulsion between the different orbitals. What we're going to do now is we're going to kind of go through some of these electron domain geometries for 2 through 6 electron domains around that central atom. And remember, to determine the number of electron domains, we count the number of lone pairs as one domain. Any type of bond, single, double, or triple, each of those is one electron domain. And so those are the things that are coming off that central atom. If we have 2 electron domains, then the electrons are in a linear arrangement, and that bond angle is 180 degrees. So in other words, we're maximizing that distance between them to minimize the electron repulsion. For 3 electron domains, then that gives us the trigonal planar arrangement. And that's what we see in the next example. And that's 120 degree bond angle there. 4 electron domains, we wind up with a tetrahedral. And in that case, all of those are equivalent. So it's 109.5 degree bond angle. for the tetrahedral arrangement. If we have 5 electron domains, that gets us to trigonal bipyramidal. And so we have what we call an axial plane. So that's the 2 that go up and down. And then we have the equatorial plane. That's kind of the flat plane there where we have 3 electron domains there. And we see in this case, we have 2 different bond angles. We have the bond angle in that equatorial plane, which is 120 degrees. And then we have the bond angle from the axial down to the equatorial, which is 90 degrees. And then finally, for 6 electron domains, all of these are equivalent. So it's 90 degrees if you measure any of those bond angles. The other thing I mentioned is that we'll use the terminology of electron domains to describe this, but sometimes you will see it called coordination number. So the coordination number of that central atom is the same term as electron domains for the central atom. But for our purposes, we'll stick with electron domains. So let's talk about how we get to a molecular geometry. Because remember here, we talked about electron domain geometries. So in each of these, we're just looking at those electron clouds. That's what the little purple lobes represent. We're not worrying right now about whether there's an atom there attached or not. Because remember, so this reflects whether it's lone pair electrons or bonding electrons. What we're really after, though, is what does the molecule look like? So those electron domains are fine, but what does the actual molecule look like? So the process to determine that is we would start with drawing the Lewis structure. So here for ammonia, we have an example. So we draw our Lewis structure. We have the nitrogen bonded to 3 hydrogen atoms. So we have those shared electrons there, those bonding electrons between nitrogen and hydrogen. And then in order to complete that octet, we have 2 lone pair electrons on the nitrogen. So that's those 2 dots, the pair of electrons on top of the nitrogen. If we look at that, we see that we have an electron domain of 4. So the 3 pairs of bonding electrons and then the pair of lone electrons. So that would give us that tetrahedral electron domain geometry. And that's what we see in the next drawing. And we see that when we draw that tetrahedral, we have our lone pair coming on top there of the tetrahedral, and we see it, the bonding electrons, the other 3 locations. So if we then go and look at the last diagram, we see just the atoms represented. So we're not representing the electrons, because when we're talking about the molecule shape, while we know the electrons are present, they're not part of the molecule shape that we're interested in. So we're only looking at, for that molecular geometry, we're only looking at the bonding electron domains. And that's where we see that now we're a trigonal pyramidal, because the nitrogen is kind of sticking up a little bit out of the plane from the hydrogens. And we'll see here in a moment that the reason for that is the influence that that lone pair of electrons has in terms of trying to minimize that electron repulsion. So let's take a look at some of these molecular geometries and how they relate to the electron domain geometry. So if we have an electron domain number of 2, then our electron domain geometry is going to be linear. And we see that there. So we have 2 bonding domains, 0 non-bonding domains, and then our molecular geometry will also be linear. So there's not really much to do on that. The other thing I'll point out is if you had a diatomic molecule, so in other words, say Cl2, for instance, that's always going to be linear too, no matter what, because there's nothing you can really do with that in terms of connecting 2 things together. That's always going to be linear. So the linear one number 2 electron domain 1, nothing too surprising there. Let's go to the trigonal planar electron domain. For trigonal planar, that would be, we would have 3 as our number of electron domains, and we see the electron domain drawing there, and that's that trigonal planar. But then we have a couple of choices. One is we can have, if all the electron domains are bonding domains. So in other words, we have an atom bonded to the central atom. And then the other choice is if we have one lone pair of electrons as one of our electron domains. So not one non-bonding domain. So in the first example, we see the BF3, we see that it also is trigonal planar when we have 3 atoms bonded to that central atom. When we look at the next example where we have 2 bonding domains and 1 non-bonding domain, so that's the NO2 ion there on the right, we see the bonding electrons going with the oxygen atoms, and then we see the lone pair signified by that kind of bluish balloon looking thing. And so the repulsion from that lone pair of electrons is what pushes that angle down and keeps the angle down and gives us the bent shape. So even though there's nothing up there, it doesn't go to linear, it stays as a bent shape because of their electron repulsion from the lone pair. Let's talk about the tetrahedral electron domain. So if we have a tetrahedral electron domain, that means we have 4 electron domains there. And if they're all bonding pairs, then we maintain that tetrahedral shape. Trigonal bipyramidal, where would have 1 lone pair, and then bent if we had 2 lone pairs. So let's take a look at that. So there's our electron domain geometry for the 4 electron domains. That's the tetrahedral. If we have bonds going off all those, for all those electron domains, we maintain that tetrahedral molecular geometry. Then when we start substituting bonding domains for non-bonding, the first case is we have 3 bonding and 1 non-bonding. Well, now we get to that trigonal pyramidal shape that we had talked about. And then if we have 2 bonding and 2 non-bonding, as designated by the 2 blue lobes for the non-bonding domains, now we have a bent shape. So it doesn't straighten out once again because of those lone pair of electrons and the electron repulsion that is associated with it. One thing I want to mention when we talk about those lone pairs of electrons is that they're larger than the bonding pairs in terms of the space that it takes up. The other thing is that because of that size, you do get repulsion, and you get a little more repulsion than you do with the bonding electrons. And what that does is that tends to change the bond angles, the other bond angles a bit. So it will decrease those other bond angles. And here we have an example of that, where if we look at methane on the left, so we have all of them as bonding electron pairs, and we have a bond angle of 109.5. So all of those bond angles in that situation are going to be equal. We look at ammonia, NH3, the next one, and we can see the 2 lone pair electrons are kind of in that loop on top there. And what we see is that because that's a little bit bigger, and to minimize the repulsion, the bond angles for the other bonding pairs those bond angles are smaller now. It's gone down from 109.5 to 107 degrees. When we have water, H2O, on the last example, then we see now we have 2 lone pairs of electrons on the oxygen. So we even have a little bit more of that kind of repulsion taking place And in this case, the HOH bond shrinks even a little bit more, and now it's down to 104.5. So, going back to this example here, we saw how as we replaced bonding domains with non-bonding domains, it impacted the shape of the molecule. So our molecular geometry changed. But the other thing it did, we see from this, is that it also changed the bond angles. And it's because of the fact that those lone pairs are a little more impactful in bond angle and repulsion and things like that than the bonding pairs are. And so I believe you saw that when you did some of your bond angle measurements and things like that in the last lab. Let's talk about multiple bonds a little bit in bond angles. So as you might imagine, double and triple bonds have larger electron domains than single bonds. So even though each of those in terms of our geometry count as one electron domain, so it doesn't matter if it's a single, double, or triple bond, it only counts as one electron domain. But the reality is that the double and triple bonds are larger domains, even though it's just counted as one. And that, just as we saw with the lone pair electrons, that influences some of these bond angles also. Because once again, you get this repulsion going on. It's a little bit bigger, and so it kind of pushes the bond angles down for some of the other bond angles. And we see an example here of that. So in this case, we have carbon double bonded to oxygen, and then we have carbon single bonded to chlorine. And we see that Cl, C, Cl, so that chlorine, carbon, chlorine bond angle is 111.4 degrees, whereas the chlorine, carbon, double bond, oxygen bond angle, that is 124.3 degrees. So just as we said that the lone pairs influence bond angle, so do if we have double or triple bonds, those influence the bond angles as well. So it goes back once again to this repulsion, this electron repulsion, and trying to do things to minimize that within the molecule. We also had talked in the past when we were starting on the Lewis structures that while we're trying to form that octet typically, there are some elements that don't obey the octet rule. And that means we can have more than 4 bonds. If we can have more than 4 bonds, then that means we can have more than 4 electron domains. So let's look at 2 other possibilities for electron domains. Let's look at 5 electron domains and 6 electron domains. If it's 5 electron domains, then the electron shape is trigonal bipyramidal. If it's 6, it's octahedral. So let's talk about those. So for trigonal bipyramidal electron domain, there's 2 distinct positions in this geometry. And so if we look at the ball and stick model below, we see that the 2 that are going vertically up and down, those are considered the axial position. The 3 that are on the same kind of flat plane in the middle, that's considered the equatorial position. And so that equatorial forms like a little triangle. The axial is the straight line up and down. When we're doing this geometry and assessing what the molecular geometry will be based on the electron domain geometry, any lone pairs that we have are placed in the equatorial positions. Okay, so when we go and we start looking at molecular geometries based on this trigonal bipyramidal electron domain configuration, if we have any lone pairs, they go on that equatorial, one of those equatorial sites. So if we follow those rules, we'll see here in a moment that there's 4 geometries that you can have in this domain: trigonal bipyramidal, seesaw, T-shaped, and linear. So here are pictures of those. So once again, for this one, we have 5 electron domains. that electron domain geometry is trigonal bipyramidal. If we have no non-bonding domains, if they're all bonding domains, then it remains trigonal bipyramidal in its molecular geometry. If we go and substitute out one of those bonding domains for a non-bonding domain, so in other words, a pair of free electrons, that's that, once again, that's that kind of blue balloon looking thing sticking out of the side on one of the equatorial sites. We now have what was called a seesaw configuration. And so if you kind of turn it sideways a little bit so that those free electrons were sticking straight up, you can envision that in your mind. It is kind of like a base with a seesaw, kind of like you would find on a kid's playground. But that's where that name comes from. The next one is we substitute two of those bonding domains for two pairs of non-bonding domains, so two pairs of those free electrons. And so now that those free electrons are designated once again by the two lobes, blue lobes on the equatorial plane, and now we have result is a T-shaped molecular geometry. And then finally, the last one is we have three pairs of non-bonding electrons, three lone pairs, and that fills up that equatorial plane. So all three of those now are lone pairs of electrons, and that leaves us with a linear configuration. Let's take a look at the octahedral electron domain. So remember, octahedral electron domain tells us that we have 6 electron domains coming off of it. And in the octahedral configuration, all the positions are equivalent. And so that just means the bond angles are all going to be the same. It doesn't matter which one you put it at, they're all the same, they're all equivalent. So there's 3 molecular geometries associated with that. There's the octahedral, square pyramidal, and square planar. So let's take a look at what those look like. Okay, so we have our 6 electron domains. That electron domain geometry tells us it's octahedral. If all of those are bonding domains, then the molecular geometry stays octahedral. If we then substitute one of those bonding domains with a non-bonding domain, so in other words, a free pair of electrons, and in this one, it's drawn with it down, that lobe pointing down. It could be on any of those positions, and because they're all equivalent, it would be the same thing. It would just be kind of rotating it around. So in that case, then you have what's called a square pyramidal. So we have 4 of those bonding domains in one plane, and then one sticking up to give it that square pyramidal shape. And then finally, if we have 4 bonding domains and 2 non-bonding domains, so that's 2 of those lone pair of electrons domains, then when we draw that, those non-bonding electrons are going to be as far apart as possible, so that puts them across from each other. So they're always going to be across from each other, not next to each other in terms of location. And once again, you could have any of these being across from each other, it'd be the same thing because they're all equivalent. So that results in a square planar shape. And so those 4 remaining bonded atoms would be on the same plane as our central atom. So that gives us a feel for what the molecular shapes are of what I would call somewhat simple molecules. So the one thing you remember on all these, pretty simple molecules, not a lot going on. The most we have is one central atom with up to 6 other atoms bonded to it. The reality is that a lot of molecules, or most molecules, are bigger than that. And so how do we figure out shapes of those? Well, the way we do that is we look at each central atom in that molecule and determine what the shape is of each of those, and then it kind of gets assembled together. So in this example here, excuse me, in this example here, the black balls are carbon, the white ones are hydrogen, and the red ones are oxygen. And so what we have here is starting from the left, we have a CH3 group bonded to a carbon. And so we have 4 electron domains. They're all bonding because we have 3 hydrogens bonded to that carbon and then another carbon bonded to it. So 4 electron domains, they're all bonding. So the electron domain geometry would be tetrahedral. And because they're all bonding to another atom, the molecular geometry for that portion is tetrahedral also. We move over to the next, and in this case, we have carbon with a double bond to oxygen. We have carbon with a double bond to whether a single bond to a carbon, and we have carbon with a single bond to an oxygen. So in this case, we have 3 electron domains. So we have 2 single bond electron domains and 1 double bond electron domain for a total of 3. So our electron domain configuration is trigonal-planar. If we think back to our Lewis structure for this carbon in this situation, we've satisfied the octet. So we've got 2 single bonded electrons, 2 single bonded electrons, 4 double bonded electrons. So we've got 8 electrons around it. So there's no free electrons on this. So it's all bonding electrons. So our molecular geometry for this part is trigonal planar as well. And then finally, the last part, we have an oxygen that's bonded to a hydrogen and it's bonded to a carbon. So if we think of our Lewis structure for oxygen, we've got 2 electrons there associated with the oxygen carbon bond. We've got 2 electrons associated with the oxygen hydrogen bond. So that's 4 electrons total. In order to make our octet, we would have 4 more electrons, so 2 lone pairs on that oxygen. So in this case, our electron domain is 4, the 2 single bonds and then the 2 lone pairs. And so that's a tetrahedral electron domain geometry. Our molecular geometry, however, this is a case of where we would have only 2 atoms bonded to it and the others are lone pairs. So that would result in a molecular geometry of bent rather than linear or tetrahedral or one of the others. So in this case, we would say we have part of it's tetrahedral, part of it's trigonal planar, part of it's bent, and then we'd kind of assemble that together to get what our shape would be. One nice thing about using these little ball and stick models is you can get a feel for what that geometry is because there is some dimensionality to it. So there's some homework associated with that first part. I'd suggest you go ahead and take a look at it and work through it a little bit. That should be helpful for the quiz next week. Any questions on this first part before I go to the next part? Okay. So we've talked about polarity of bonds and things like that, but really what we're after is polarity of molecules. And how do we determine that? Well, we had talked about, first of all, is it a covalent bond or an ionic bond? And we said if it's a metal, a general rule of thumb is if it's a metal with a nonmetal, it's probably ionic. If it's a nonmetal with a nonmetal, then it's probably covalent. And so it's those covalent bonds that we're interested in determining if they're polar or not. So the first thing we do is we think back to our electronegativity chart. Remember, that's where we said in the upper right-hand corner, those are the elements that are most electronegative. And if they're very electronegative, they want to pull that negative charge towards them. So if we look at this and we say, Does it have a dipole? Is the bond polar? So in other words, do we have a shifting of that charge? If we look on that electronegativity chart and see the values are pretty similar, then we would say it's a nonpolar bond. And if the bonds are nonpolar, then the molecule is going to be nonpolar. If we look at that bond and we say, according to our electronegativity chart, that we do have a shifting of those electrons. In other words, they're not sharing them equal between the atoms. Then we have a polar bond, but then we need to assess all of the bonds that are taking place to see if the molecule is polar or nonpolar. So we'll look at an example here in a moment, but what you're doing is you're looking at all the bonds that go around that central atom and seeing if each individual bond is polar or nonpolar, and then you're kind of adding up the total. So let's take a look at how we do that. Before we do that, I do want to point out that the dipoles and the associated dipole moments are vector quantities. And when we say something is a vector quantity, what that means is it has a magnitude and it has a direction. So in other words, it's not just the number, but it's also the direction that the number goes in. And so for us, when we talk about the direction, and this is why you remember we talked about drawing that with the little plus on one end and the arrow pointing towards the more electronegative element. That's the direction. The direction is saying which way is that are those electrons kind of being pulled, and then how strong is the pull. So let's take a look at this. So here are two compounds. One is nonpolar and the other is polar. But what you'll notice is each of them have polar bonds. And so this is how we get to something that even though it has polar bonds, it can be a non-polar molecule. So let's look at CO2, the one on the left first. We have the carbon atom with two double bonded oxygens. And so we know from our electronegativity table that oxygen is more electronegative than carbon. And that's what that 3.5 and 2.5 numbers underneath the atoms designate. And so if we're going to represent that dipole, we would put the little plus over the carbon and then have the arrow pointing towards the oxygen. And we have that going both ways. And so this is where, by knowing the shape of the CO2, and this goes back to our molecular geometry, how we figured that out, we know that it's a linear molecule. And so what this means is that the dipole from one carbon to an oxygen double bond, we see that going, kind of an arrow going to the left. Then the other dipole for the carbon and the oxygen double bond, we see that with the arrow pointing to the right. So they're both carbon-oxygen double bonds, so the magnitude is going to be the same. But they're actually, because it's a linear molecule, they're pulling on it equally across that. And so what that tells us is that overall, they cancel out. So we look down at the color plot down at the bottom. And once again, the red means that's higher electron density, blue means lower electron density. So we look at that color-coded plot at the bottom, and we see the blues in the middle, where the carbon would be. And that makes sense because we're saying that's less electronegative. So the electrons are going to be pulled more towards the oxygens. And we see both ends, it's kind of that reddish, yellowish, orangish, which we say is the higher electron density. So from a simple bonding perspective, it all makes sense. But think of it as, in this case, if the oxygens were two people kind of pulling on a rope, they have the same amount of strength, so they're going to pull, and the end result is nothing really goes anywhere. So they cancel each other out. And that's how we get an overall dipole moment of 0 and winds up that CO2 is nonpolar. On the right-hand side, we have water, and water is a very polar molecule. Well, if we think back to its molecular geometry, it is not a linear straight molecule. And that's because in this case, we have the oxygen there in the middle, and we have the two hydrogens on it. They're single bonds. If we think back to our Lewis structure, we know there are additional free electrons around that oxygen. So we've got two electron pairs around the oxygen. That forces the shape down into this bent shape. And so now when we do our individual dipoles, we have the plus on the hydrogen, the arrow pointing towards the oxygen, okay, because oxygen's more electronegative than hydrogen. So we've got two polar bonds going in that direction, and we see that it becomes an additive effect. So those two are both going towards it. So on the CO2, they were pulling away, kind of canceling each other out. Here, they're additive, and that's where you can see the overall dipole moment arrow, which is that darker red one, kind of below the oxygen pointing upwards. That's a bigger, broader arrow to signify that that's a kind of an additive effect of the electron movement, electron sharing rather. We go and we look at the color-coded electron density down at the bottom, and we see that, as we would expect on that oxygen atom, there's a higher electron density. There's less out on the hydrogens because of that difference in electronegativity. So when we look at those polarity issues, we want to look at the individual bonds and then use that information to determine if the molecule is polar or non-polar. And this is where knowing that molecular geometry comes into play, because by having that molecular geometry information helps us understand kind of what direction those dipoles are going in. Here's some more examples of compounds that have polar bonds, and sometimes you wind up with a non-polar molecule, and sometimes it remains a polar molecule. And so let's just take a look at this for a moment. So in the first one, BF3, we have boron as the central atom, and then we have 3 fluorine atoms attached. We know fluorine is more electronegative than boron, and there we have those electronegativity values listed under the atoms. And so each of those is directionally pulling electrons away from it. Because it's a symmetrical molecule and it's all kind of pulling in the same amount, then it all essentially cancels out and you wind up with it being nonpolar overall for the molecule, even though you've got 3 polar bonds. The next one, HCl, we have the hydrogen on the left and the chlorine on the right. The electrons are being pulled in direction of the chlorine because it's more electronegative. And so that's telling us that for this molecule, it's a polar molecule. CH3Cl, we have the carbon as that central atom, the black one in the middle there. We have the 3 hydrogens attached. And if we look at hydrogen versus carbon, there's really not a big difference there. So you don't see a dipole created there. But the difference between the carbon and the chlorine is a little greater, so we do get a dipole there. We see it goes in the direction of the chlorine, and so that overall winds up being a polar molecule. NH3, we have the nitrogen bonding to 3 different hydrogen atoms. The nitrogen is more electronegative than the hydrogen. So we have dipoles going towards the nitrogen, and that'll be additive, and we wind up with a polar molecule there. And then finally, the last one we'll look at is carbon tetrachloride, CCl4. We have those carbon chlorine bonds are all polar because chlorine is more electronegative than the carbon. But because of the geometry of the molecule, they're all kind of canceling each other out. They're pulling in the same magnitude, just opposite each other, and the end result is carbon tet is nonpolar. So just one little trick I'll tell you is we see that third one, the ammonia, the NH3. If something has nitrogen in it, it's almost always polar. Just a little rule of thumb there. Okay, let's talk about valence bond theory for a bit. So in valence bond theory, we're talking about the electrons from the two atoms are occupying the same space. And when this happens, we call it an overlap of the orbitals. And so we have this shared space between the two electrons. So we have their opposite spins, and that's what forms the covalent bond. Because the electrons are in the overlap region are simultaneously attracted to both nuclei. So they're kind of in this overlap space, and so they're being attracted to the nucleus of each atom. This holds the bonds together. This holds the atoms together, and that's the formation of the covalent bond. So we have a couple examples here. The first one are two hydrogen atoms to form H2. And in that case, you have a 1s electron from each, and we have this overlap area, and that's where we form that covalent bond. The second one is HCl, and so we have a 1s electron from hydrogen interacting with a 3p electron from chlorine, and we have that overlap there to form the covalent bond. And then the third example is Cl2, so we have two chlorine atoms bonding together, and we see the overlap of the 3p orbitals there to form that covalent bond. So when we talk about this overlap, what we're talking about is finding that place in the energy diagram, and that's what we have down on the bottom here. And we want to be at the lowest energy because that's where it's going to be most stable. And so we're looking for the place in terms of the distance between the nuclei. And in this example, it's the hydrogen-hydrogen. So it's two 1s electrons coming together. And so this is where we think about those different interactions that you can have. You have the repulsions of the electrons to worry about. You have the attraction of the electron to the nuclei. You have some internuclear repulsions if things get too close. So we look at this energy diagram, and remember, the most stable place is always the lowest energy. So as we kind of go across, we start on the right-hand side, and we see if we're too far away, the energy remains high because we're not getting the proper attraction there. As we get closer, the energy starts to go down. We get to that sweet spot there where we've kind of balanced the attractive forces with repulsive forces, and that's where we start to see that overlap that we talked about. If it starts getting too close, now we don't have so much the problem of the electron repulsion with each other. We now have nucleus repulsion. So in other words, the positive nucleus of one repulses the other based on that positive nucleus. So this energy diagram shows us that there's a sweet spot there in that distance, that bond distance, where all of these interactions, the good ones and the bad ones, are kind of balanced out properly. There's something that we call hybrid orbitals. And so hybrid orbitals form by mixing, we'll call it mixing atomic orbitals to create new orbitals of equal energy. And remember a while back when we were talking about energy levels, we said that if you have orbitals that are of equal energy, that's called degenerate orbitals. So this process where we combine some orbitals so that we have several that are of equal energy, that's called hybridization. Hybridization is kind of a math thing, so we're not going to get into the math, but we are going to talk a little bit about what we call these orbitals when we generate hybrid orbitals and mix them. So let's look at sp hybridization. And so in this example, we're going to we'll take a look at the orbital diagram for beryllium. And so if we look down at the bottom at that first electron configuration, we see we have two 1s electrons and two 2s electrons. Well, beryllium actually makes electron deficient compounds with two bonds. And the reason for that is what we call is sp hybridization. So in other words, what we do is we say we mix one s orbital and one p orbital. So that's represented here in that second one, where we say we're going to look at it, instead of being two electrons in 1s and two electrons in 2s, we're saying it looks more like two electrons in 1s, one electron in 2s, and one electron in 2p. The 2s and 2p in this case have the same energy levels. That's that degenerate thing we just mentioned. And so that's where we write it as a hybridized orbital. So instead of saying a 2s, one in 2s and one in 2p, we say there are two sp orbitals. And so those are equal energy, no difference in energy, and that's how we were able to explain beryllium with that two bonds. Let's take a look at what this is visually. So we said that if we mix the s and p orbitals to get this sp hybridization, we get two degenerate orbitals. And so down at the bottom here, we have one s orbital, that's the sphere, and we have one p atomic orbital, that's the two lobes. And so if you add that s orbital to one of the lobes of the p orbital, then we wind up getting this bigger looking lobe here on the one side. And those are our two sp hybrid orbitals, okay? Because remember we said we're going to have two orbitals now instead of a separate s orbital and a separate p orbital. So we've got two orbitals that are the combination of those. And so if we overlay them, then we see that it just looks like kind of a bigger version of the p orbital. Let's see how this works then. So the two degenerate orbitals would align 180 degrees from each other. So in other words, they'd be in a linear fashion. And if we went through the geometry of compounds like beryllium fluoride and things like that, and looked at the VSEPR through the VSEPR lens, then we would see that it's linear. And so here's an example of that. So here's the beryllium with those two sp hybrid orbitals interacting with and bonding to two fluorine atoms. And so we see the fluorine, its 2p atomic orbital is overlapping with those sp hybrid orbitals from beryllium to form that beryllium, fluorine, those two bonds. Let's take a look at sp2 hybridization. So in this case, we have 3 electron domains. So we have one s orbital, and then we have 2 of the p orbitals. And remember, with the p orbitals, we had 3 different orientations. We had along the x-axis, the y-axis, z-axis. So let's take 2 of those orientations, do that same combination we did with sp, except now we're going to do it an extra time with the with 2 p orbitals instead of 1. And that results in 3 hybridized orbitals. along 3 different planes, and that's what we see drawn here under the hybridization. We put that together, just looking at those large lobes, and we see kind of a triangle type shape with the sp2 hybridization. Once again, I think you looked at some of this stuff in the lab, that last lab, of equating these hybridizations with different shapes. Let's look at sp3. So here, carbon's the example for sp3, and we have our s orbital. As I said before, the p orbitals, we have those 3 dimensions along the x, y, and z axes. We'd go ahead and do that hybridization, and we see that of that bigger lobe going in each direction in this, and now it's like a tetrahedral look. And then we combine all those, and we have this hybridized tetrahedral type of arrangement, and that's the sp3. So let's take a look at water for a second to see why its angle is not 90 degrees, that it's 104 degrees, 104.5. So if we draw the Lewis structure to assign Vesper, it becomes bent. So we talked about that before. We've got those lone pairs of electrons and that. So it's electron configuration 1s2, 2s2, 2p4. If it shares 2 electrons to fill its valence shell, they should be in 2p. So if we look at this drawing at the bottom, we see the oxygen bonded to hydrogen. So that's a single bond there. But then, as we talked about earlier, there's 2 lone pairs of electrons here on that oxygen. And so what we wind up with is we wind up with sp3 hybridization, because we've got 4 spots there. So because of that sp3 hybridization, we wind up in this tetrahedral look, and that's the reason why the bond length angle is 104.5 rather than 90. Just wanted to mention that we've talked in the past about hypervalent molecules, and those hypervalent molecules were the ones that have more than an octet. So in other words, we violate the octet rule. If for the valence bond model, we'd use the d orbitals to make more than 4 bonds. And this view works for period 3 and below. Remember, period 3 is the rows, so it's the 3rd row on down. In theory, theory suggests that the energies needed would be too great for this to happen, and so the bonding is a little more complicated than that. And we're not going to go into it. We're just going to mention that this bit about the hypervalent molecules. So just to kind of summarize what we were talking about with hybrid orbitals, is that in order to investigate that, you would draw the Lewis structure, you would use the Vesper model to determine that electron domain geometry around the central atom, and then you would specify hybrid orbitals needed to accommodate the electron pairs based on the geometric arrangement. So it's that kind of combining it to satisfy what we do in the Vesper model. So that's how you get the SP, SP2, SP3 stuff. So let's just go through this again with the pictures so we can kind of see what it looks like. So if we have want to combine an S and a P, that would result in 2 sp hybrid orbitals, and that would give us a linear geometry. If we combined an S, a P, and a P, that would give us 3 sp2 orbitals, and then that would be trigonal planar. If we have an S, a P, and a P, we'd have 4 sp3 orbitals, and that would result in a tetrahedral geometry. So once again, there's some homework associated with this. Take a look at it, and we'll move on now to, unless anyone has any questions on that last part, we'll move ahead to the next section. Okay, so let's talk about types of bonds. We've talked about single bonds, double bonds, triple bonds. How do we account for a double or triple bond? If we only talk about the hybridized orbitals, it doesn't really explain what's going on with the double or triple bond. If we have orbitals that are not hybridized, then we get a different type of overlap of the electrons, and we'll see some figures of that here in a moment. When we think of two types of bonds, we have sigma bonds, which are single bonds, and we have pi bonds, which are triple or double bonds. So those single bonds, we can explain that with hybridization. The pi bonds aren't explained that way, and we'll see in a moment what that means. So sigma bonds, if we look down at the bottom, we characterize those as an overlap, a head-to-head overlap. So in this example, we have two pi bonds overlapping. So we see the heads of the pi bonds overlapping, and you see that kind of darker overlap period there. So that shows us the electron density there goes along the axis of the two atoms, and we see that overlap in between them to form that sigma bond, that single bond. Pi bonds are a little different. Their electron density is above and below the internuclear distance, so that sigma bonds overlap along that internuclear axis, pi bonds above and below. And so it's kind of like a sideways thing. When we talk about the bonding in molecules, let's kind of walk through this example here. So the one on the left is C2H2, H4. The one on the right is C2H2. And so the one on the left has a carbon double bonded to another carbon, and then each of those carbons has two single bonded hydrogens. The one on the right is carbon triple bonded to another carbon, and each of those carbons has two hydrogens. So on the left there, so let's take a look at this. Single bonds are always sigma bonds. Multiple bonds have one sigma bond, and then if it's a double or triple, those additional bonds are pi bonds. So starting on the C2H4 on the left, we see we have a carbon atom bonding to another carbon. And so there we have, the next we go down to, now we've added the hydrogens to the carbon. That's the little blue circles on the left and on the right. That represents the sigma bond between carbon and hydrogen. And then finally we go to the bottom, and now we see the pi bonds, that's the stuff that's kind of going over and below the sigma bond, kind of the light pink color. So that tells us that we have a carbon-carbon pi bond. And we also know from the beginning when we started looking at this, we had a carbon-carbon sigma bond. So that carbon-carbon sigma bond, that is the hybridization bond. The pi bond, though, is not hybridized. And so that accounts for the different above and below that we talked about back here. So there we talked about how the pi bond is above and below the internuclear. The sigma bond is along the internuclear axis. On the right-hand side, where we have a carbon, the C2H2, we have the carbon bonded to the other carbon, and that's an sp hybrid orbital, because we're going to have one hydrogen bonded to it and then the carbon, so we have the two. And those form sigma bonds. We see in the next one down, we see that carbon-hydrogen sigma bond. So there we've got the carbon-carbon sigma bond and the carbon-hydrogen sigma bond coming out of those hybridized orbitals. But then we have the unhybridized 2p orbitals come into play for the two carbon atoms, and we can see two of those pi bond situations. We have the ones that are above and below, just as we had on the one on the left, and then we have pi bonds that are kind of coming out of the screen towards us and back into the screen the other way. You can kind of see that in the back there. So what this tells us is that this has one sigma bond, it has two pi bonds, so it's a triple bond here. The one on the left, the first one we looked at, had one sigma bond and then one pi bond, so it's a double bond. So once again, I think you looked at this in the lab. This is how we account for multi-bonds. They're not hybridized. Excuse me, they're not hybridized. You have that sigma bond that's hybridized, but then the pi bonds are not. It's just that p orbital interaction in this case. When we talk about bonding electrons, whether they're sigma or pi, if they're specifically shared between two atoms, we call that localized electrons. Oftentimes, we can't describe the electrons as being specifically shared between two atoms. And that's where we start talking about resonance structures. And the one that you did some work on in the lab was the benzene molecule. And so in that case, you have the electrons, which are a little more spread out. They're not just on the two atoms. They're shared by more than two atoms. And we call those delocalized electrons. So let's take a look at what that looks like in the benzene example. So benzene has 6 sigma bonds. Okay, so that's that overlap bonding, and we see that in the first picture there in the upper left. So we see those sigma bonds forming through the overlap. It also, each of those carbons has a p orbital on each one of those. So that's the second diagram you see. You see the picture of the p orbitals. We said just now that when we're talking about multi-bonding, so we say we have a sigma bond, and then everything after that is a pi bond. So now the third, that if we go down here, this is the next row, we see 2 configurations for localized pi bonds. So that's that bonding that goes on above and below the axis. And we see it here on the left and on the right, just kind of rotated basically, the 2 versions of it. But really, when you combine those two, what you're really talking about, and this is the resonance drawing, you're talking about kind of a ring of electrons above and below that linear plane there. And so it's that that's where we call it delocalized. So it really isn't a localized picture of how the electrons are being shared like we see on the left. It's more like this resonance structure, which kind of shows it all kind of more spread out more evenly around the ring. And if you recall, when you measured that, the bonding information, the bond lengths didn't equal a single or a double. It was kind of in between, if you recall your values. And that's because of this delocalization that we see here. Let's talk about molecular orbital theory for a bit. So if you recall, we had earlier said that we can use wave properties to describe the energy of the electrons in a model, in a molecule. Molecular orbitals, so up until now we've been talking about atomic orbitals. Molecular orbitals have a lot of the same characteristics as atomic orbitals. So you can have 2 electrons per orbital. Electrons in the same orbital have opposite spin. There's definite energy levels associated with the orbitals. And you can visualize the electron density by a contour diagram. So let's take a look at molecular orbitals here. While they're very similar to atomic orbitals, they are different because we're talking about the entire molecule, not just a single atom. When we have 2 atomic orbitals that overlap, then we get 2 molecular orbitals are formed. We call one of those a bonding orbital and one an anti-bonding orbital. The bonding orbital are constructive combinations of atomic orbitals. And so what that means is it's a more stable situation. And that orbital will be lower energy, because remember, we always want to be at the lower energy to make something the most stable. The anti-bonding orbitals are destructive combinations of the atomic orbitals, and they have something called a nodal plane. And that means at that nodal plane, the electron density is equal to 0. Because of all this, they're higher energy and they're less stable. So in order for a compound to exist, it needs to be in the bonding orbitals. If it's in the anti-bonding, then it's not going to happen because it's just less stable, or it may just be there for a short period of time. So let's take a look at the combination of 2 hydrogen atomic orbitals. So here we have it where we have a 1s electron from each of the hydrogen atomic orbitals, and those combine to form our molecular orbital. So on the bottom there, we have the 2 overlapping in a constructive manner. And so we have the electron density in between the nuclei. So in other words, it looks like a bond to us. If we go to the higher energy combination, that's our non-bonding orbital, and it's a destructive combination. So then in the areas in the middle, we have no electron density there. And that's that nodal plane that I mentioned. So when we draw that non-bonding or anti-bonding orbital, it's the sigma with a little asterisk or star over it. And so what we can do now is we can draw what we call a molecular orbital diagram or an energy level diagram, either one you can call it. And so what this does, it shows us how orbitals from atoms combine to form molecular orbitals. So once again, this is our H2 example. As we said before, we have 1 electron from one of the hydrogen atoms, another electron, opposite spin of the other hydrogen atom. We draw this molecular orbital stuff in the middle. So down below is the bonding, above is the anti-bonding. And so we go and we fill in those orbitals just as we would fill in any orbitals, 2 at a time. So we fill in the bonding one, that's the the 2 electrons you see there in that sigma 1s level. And so we can calculate something called a bond order. And so we want the bond order needs to be a number, or we don't have a stable molecule. It needs to be 1 or 2 or something like that, or we don't have a stable molecule. And the way we calculate that bond order is we have the number of bonding electrons. In this case, it's 2. The number plus, or rather minus the number of anti-bonding electrons. In this case, there are no anti-bonding electrons because we only had 2 to work with, and that filled up the bonding level. So 2 minus 0 is 2 divided by 2, and we wind up with 1 bond. So it tells us the bond order is 1. Since we have a bond order value of 1, that tells us that it's a stable molecule, and so that H2 exists, which is good because we know that it does. So I'm going to stop there for today. We'll pick up the rest of this next week. Any questions on anything so far? Okay, I just want to repeat again, for those of you in my lab section this afternoon, please log on and take the Gen Chem lab final online this afternoon during the lab period. For next week on Monday, we will have an exam on chapters 7 and 8. So there will be no class on Monday, just during class time, log on and take the exam. If you're not in my lab section and you have some questions about the final, please contact your instructor. All right. If there's no other questions, that'll be it. Thank you.